So I have a joke to start. It's a database joke, and even better, it's a NoSQL database joke, or at least I hope it'll be a NoSQL database joke. So 3 relational DBAs walk into a bar. They walk into a Couchbase bar. You might ask, what's a Couchbase bar? I don't know, but it's important for the joke. So these 3 relational DBAs are in this Couchbase bar, and they're talking to each other, and they're looking confused, scratching their heads, shrugging their shoulders. And after a few minutes, they exit the bar. So the question is, why did the 3 relational DBAs exit the Couchbase bar?
They couldn't find a table.
Got it! They couldn't find a table. Because they couldn't find a table. It's very corny, I know, but you got to try. My name's Mike Ryder, as Mark said, and I'm from UPS. I'm a data architect at UPS. We have implemented a few projects on Couchbase in the last couple of years, and I'm here to talk about one of those projects. My colleague Constantine has also given this presentation once, so you're getting it for the second time. And the objective of the implementation that we did was to try and manage the cost and the manageability of Couchbase for a reasonably large implementation and determine how best to control node sprawl as it's associated with that implementation. What are we going to cover today? We're going to look at the use case. We're going to look at the problems that we've identified that are associated with node sprawl, the architecture choices that we made and why, the wins that we, as an organization, believe we have just discovered by using the methodologies that we did use. We want to talk quickly about some of the features we'd like to see added to Couchbase, and some of those have already been added to Couchbase. And lastly, just the lessons learned from this experience that we went through. So first of all, UPS. I'm assuming most people here know what UPS is. It's a pretty diverse organization, large organization with a lot of different products, but our main product is pretty simple. We get a package, we pick it up, we move it somewhere, we put it down. That's it. That's our business model. It's very simple when there's only a small number of packages. It gets more complicated when you've got millions of packages every day, and it gets more complicated when the data that's associated with those movements becomes larger and larger. So we want to know when we're picking it up, how big it is, where we're moving it to, when it gets there, and then we're going to move it over here as well, and we're going to move it over here, and we're going to take it to this person, and so on and so forth. So there's potentially a lot of data associated with that operation. So what we have here is just a little use case from our package tracking capability on the web. It's available to all our customers, and just quickly we'll run through, hopefully, yeah, there goes my little cursor moving along. So this is using what's called My Profile or My Choice. We're tracking a package. After you've logged in, it'll bring up your shipments and put them in a calendar view for you, which is coming up now. This is a demo, a dummy shipment that was thrown into the system for us. They wouldn't let us use live data for whatever reason. It'll show us the details about what's involved with that package, where it's coming, where it's gone from. We can change our delivery, set up delivery alerts if we want to, and we can look at another level of detail should we want to do that. And that's what we've got down here, and I'll scroll down. So this is the data that we're essentially trying to make available to anyone in the world. And we've got to make it available quickly, we've got to make it available to scale, and that's the challenge that we're trying to deal with. We've been around as a company since 1907, and we've brought in technology over that time to help us do that. So while we were thinking about where we go in the future, we wanted to look at the requirements that were involved with package tracking and and to make sure that the solution would fulfill those requirements. And those really involved in keeping track of inquiries and changing state of billions of packages over a reasonable period of time. We needed to be very performant, so we need to get those results back extremely quickly. As our volume and our customers and our number of packages and the data in the packages increases, we need our back-end systems to be scalable to manage that. And we needed also to be very flexible because we have changing data elements popping up consistently. We can't afford to take a lot of downtime and a lot of effort to include those into our data requirements. We have billions of documents that we need to deal with, tens of terabytes of data, tens of thousands of operations per second, and 30 plus millions of document inserts and updates per day. How do we manage this? So, taking a slight history lesson here, we started off with relational technology, basically as soon as it became available, and to some extent we're still dealing with relational technology, mainframe technology mostly, but as I mentioned, as the number of data points increases, the amount of data increases, the number of packages, and so on, that becomes tough to maintain. So we call this generation 1, where we just have the monolithic database in the background and we have our applications calling that data. To try and alleviate some of that cost and some of that latency or potential latency, we included in generation 2 a write-aside cache at the application layer so that we don't always have to go back to the database. We can pull that information in from cache when necessary. This has served us pretty well, but again, data increases, requirements increase, latency increases, or we need latency to decrease again. So we have moved, in fact, to generation 3, where we bring in a NoSQL database. We've chosen Couchbase for various reasons. We still have the relational database sitting on the bottom here, but we have a pub-sub architecture where all of the messages, all of the data changes go to both the relational database and the Couchbase database. And Couchbase is what the client side goes through the network or the cloud to pull out the relevant data that they're looking for. The difference between the Couchbase side and the relational side is that the way that we put it is that the data sleeps in relational. So nobody's really looking at the relational database unless it's an exception, but it plays in Couchbase. So Couchbase is typically a shorter lifespan of data. We're only interested in a relatively short period of time, but that's where all of our, well, almost all of our activity comes from. The relational database is still considered our system of record, and Couchbase is considered the system of engagement, which was last year's buzzword for Couchbase Connect. So in determining how we would migrate from our relational system or our mainframe system to a Couchbase system, we needed to figure out how we deal with the number of nodes. How do we get the number of nodes that were going to be sufficient to support the application, but yet still prove economical and manageable from a business perspective? We came up through various mechanisms that I'm not going to delve into. There's a bit of detail on this page. But basically, we realized that we don't need to keep all of our data in memory. We'd be fine with a minimum amount of data in memory because, again, we're only looking at the very recent data for 98% of our queries. So the last couple of weeks. We don't typically go past that. And yet we wanted to keep 4 months worth of data in Couchbase if we could. We'd actually like longer, but that didn't prove to be financially viable. We determined that we would build our nodes with a 256 gig RAM configuration, which fitted nicely with our 15%-ish resident in-memory documents in memory. Smaller the RAM, the more nodes we needed, of course. And we recognize that even though we have smaller nodes, we are going to end up with some over allocation and compute. So we went through and we figured out how many nodes we would need to manage the amount of data that we're dealing with, which was something around the region, I think, of about 15 billion documents. And we were up at around about 100 nodes. 100 nodes is tough. Couchbase is horizontally scalable, but there are practical limits to that horizontal scalability. The recommendation was not really to go over 40 nodes. So we were having issues on how we would deal with that. One of the factors that increase the number of nodes is the fact that when you get over 10 nodes in a cluster, the recommendation, strong recommendation, is to make sure that you have 2 replicas rather than 1 replica to allow for multiple concurrent failures. So if we could rip that back to a scenario where we didn't have to have 2 replicas, that would effectively reduce our number of required nodes by about 1/3, which we were able to do, and I think by working a couple of tricks. The first one is to be able to use compression, and the second one is to be able to use sharding of our database, so logical physical clusters, but logical shards within those clusters. So looking from a compression perspective, we realized that the requirements for our application didn't require us to do a lot of querying on very many elements within the document. Only in this example, it's a very small subset of the document, but the highlighted elements in there are really all that we need to query against. So all the rest of the document is just payload. We realized that we could compress that payload before we ingest the document and then retrieve that full compressed document, uncompress it, and do whatever we need with it at that point. So as I said, we had around about 100 nodes for our projected cluster size. That was going to be way too much in terms of the economic reality for this project. The compression idea is to compress the payload. We would do it before ingestion because we wanted to make sure it was compressed in memory as well as on disk. And then we also had a sharding idea. So the way that we do that is to have multiple physical clusters and then logical shards within those clusters that make up one full cluster. Each of the physical clusters ended up being, I believe, 8 nodes. So we have 24 nodes for our logical cluster made up of 3 physical clusters, and then I think it's 16 shards across those 3 physical clusters. That does add a level of complexity to the scenario, and that complexity is really pushed to the application layer, where the application has to create their own algorithm to manage where those documents go across those shards. But it does also give us flexibility in that we can move those shards from cluster to cluster to manage the load that we have. And as it turned out, the application, when they built the algorithm to distribute the documents among the shards, they made an error, and we actually ended up with 2 shards that were permanently empty. And rather than go back and reshard everything. We actually dealt with that and just moved to shards so that we didn't have one cluster that was lighter than the rest of them. So from a perspective of deploying within UPS, what we consider to be wins are the fact that we didn't have to deal with a 100 node cluster. The problem with the 100 node cluster was one of cost and two of manageability. How do you manage dealing with 100 node cluster? Our DBAs didn't like that idea at all. So we managed to chop that down to around 20. I believe it's 24 now, by doing 80% data compression. It allowed us, by sharding to logical clusters, well, it also allowed us to be able to do parallel maintenance activities. So instead of having one big rolling upgrade, we can now have 3 smaller rolling upgrades, which helped our DBA colleagues. Importantly, it made us able to keep our replica count down to 1 without compromising our durability. And it obviously reduces our infrastructure footprint and allows us a certain amount of headroom to allow for growth, because our business is growing. The number of packages you're buying from Amazon is increasing, and that just keeps on going year after year, as well as the amount of data points per package. It just keeps building and building and building. A few lessons that we got from working through this process are features that we'd like to see or have seen included into Couchbase. The first one is the native in-memory compression. We requested this back in May of 2017, and it is now in Couchbase 5.5. It's using the Snappy library. We would still ask the Couchbase folks in the room to improve that compression. The compression ratio that we've seen by doing the limited testing is pretty poor compared to other compression out there. It would be great to have better compression. But the nice thing about using this native compression is that we can now query that document if we had the need to do so. Second thing we'd like to see is the ability to move the management of sharding out from the application layer to being part of the SDK. I don't know when that will happen, but we've made the request to Couchbase, and hopefully that will happen at some stage. The third thing is a node density request. We've made this request out to Couchbase, and I know Couchbase is an in-memory first database, and that is your ethos, and I understand that, but there are some scenarios where it doesn't really make a lot of business sense to have that data, all of that data in memory, or even 15% of it. We might want to go down less than that for certain use cases. And once again, that's not on the roadmap yet, but we've made the request. So lessons learned from what we did. We need to consider service requirements, and so that's our data size, the performance responsiveness, document size, number of documents, all of those kinds of activities, statistics. The best practices that Couchbase gives us, that's important to know how much RAM we need per node, the number of replicas, how many nodes that we can build out before we have to increase the number of replicas, and those kinds of parameters. The deployment considerations may drive data sprawl. We can limit the RAM limiting RAM leads to more nodes, and more nodes leads to the requirement for more replicas, and that vicious circle just keeps on going. And the number of nodes, of course, as we increase, the number of nodes, it costs more, and that impacts the business justification for the project, and that can lead to a suboptimal alternate technology being selected. And then finally, the possible answers to node sprawl, the two things that we've come up with which have worked is compression and sharding across multiple clusters, and they've both worked very well. And that's it, and I'm almost on time.
You got about 4 minutes.
All right, I got a couple of questions out there. Yeah, oh, let's get the microphone.
There you go.
Thank you. So I have a question on your architecture slide, so if you can go back to that
Sure.
slide where you were showing the event sourcing from the relational database.
Event sourcing from the, oh,
Yeah, yeah.
this one here?
This one, yeah.
Yeah.
So it seems like most of the transactions are read-only from the client side because it's just a tracking
Yes,
queries, right?
yes. Well,
So-
that is true. There are multiple customers out there for this data. External customers are certainly largely, as you say, read-only, but there are some internal customers that may not be read-only. They may do updates and changes.
So my question is, it looks like to me that the question is, why did you not use in-memory database as compared to the Couchbase? Why do you have to go to the Couchbase rather than just using an in-memory database that just gets fed in by the events from the relational data store?
The main reason I believe that we went into Couchbase was because of scalability, because of manageability and scalability. There are certainly other solutions that would work, but Couchbase was a technology that we were interested in. We had brought it in for a couple of other small projects, and this seemed like a good fit for a Couchbase solution. One of the things that at UPS we try to avoid is bringing in too many technologies. So if we can limit the number of technologies that we have, we will make every effort to do that because we need to support it. We need to know, how the quirks and the intricacies of each of these technologies, and we need to build up relationships with vendors and so on. So that's primarily why we went down the Couchbase road.
Hey, so regarding the sharding across multiple clusters, I think you mentioned that in context of upgrades, like doing upgrades on your clusters. So when you upgrade one single cluster, you can do a rolling upgrade of each individual node, and only when the last node is upgraded does the cluster kind of jump to the next version. But how do you manage that for multiple clusters? Because it's not going to be an atomic thing.
You're right. I mean, in theory, we would be able to do a rolling upgrade and have, if we had, say, for 3 physical clusters that make up the one logical cluster, we could have one of those physical clusters at one release level and 2 at a different release level, and that would be a bad thing. So that's a process management activity that we internally have to maintain. It's not something that would be potentially part of the addition to the SDK in Couchbase that would handle that. But at the moment, those are, from a Couchbase perspective, they are physical clusters. So that potential for disaster is out there. Not disaster, it wouldn't be a disaster, but it's certainly not an ideal management solution.
You got time for one more? Yeah.
Yep.
What is your cache to resident memory ratio?
Cache to resident, so
The documents in the
working
cache.
set?
Yeah, how much percentage of the documents are in the cache?
Yeah, so we're aiming for 15%, which is the minimum that Couchbase recommends. When our clusters were badly imbalanced, we were significantly lower than that on, I think, 2 of the clusters. And to be fair, it wasn't just because of the imbalance, it was also because it's extremely important to estimate appropriately when you size your cluster. And we had estimated, I think, underestimated about 20% in the number of documents we'd be dealing with, and we underestimated by 25% the average size of the document, which you don't realize that until you're starting to populate the environment, and it gave us a problem. I think we were down to 7 or 8% in certain on certain clusters, which was not a sustainable number. And so we had, I think at that stage we had 6 nodes per cluster. We now have 8, which is bringing us up to 15%, which is where we want to be. And we have some headroom to expand that, to keep that number as time goes on. Yeah.
From a relational database perspective, I'm assuming that's Oracle. So when you move to Couchbase, how was the transition done? How was the migration path? Because RDBMS is rows and columns, Couchbase is KBS. So how was that done? Can you throw some light? I'm looking at 100 nodes. The data size seems to be pretty large.
Yeah, so I assume you're talking about migrating the existing data from, yeah, so we didn't, is the short answer. We started the cluster from scratch, and we had built the application to start populating the cluster from a certain date. So we built that, because it's only 4 months worth of data, we had enough lag time to be able to say, okay, we're going to start from today, and then, September, and then by February we'll be in production. So that was our migration. Okay?
Thanks so much, Mike.
Thank you very much. Appreciate it.